Hi, this is the addendum for discrete random variables for HL. We're going to start with a problem which, if there's too much in here that's new and is difficult to understand, don't worry about it too much. But this is kind of an introduction to some of the things that you're going to do in the option book later. First of all, they all of a sudden lay on you that a power series has this appearance here. A power series is it's a sum of a bunch of different terms, and the terms have a pattern, and the terms have a pattern that can be defined using a summation symbol, like here. And this particular series is close to the function e to the x, okay? And we're going to learn all about this in the green book, so you can just take their word for it for now, okay? And then they say, if you know that this series here is equal to e to the x, where do you see how the yellow x appears in the numerator of the term? Okay. So the x is the base of the exponent. And so every time you see x here, it's the same x as here. Okay? So basically this is a definition that doesn't depend on x. It can be any value of x. Okay? Now here they give us a very specific value of the power series. And if you look at this, you can see that here the x refers to 0.2, right? Because 0.2 is the base of the exponent. So, in this case, x is equal to 0.2. Do you see how the green part matches up also? N factorial. So like the denominator of this series here, the denominator is always factorial, just like here. So basically the yellow part is the x to the exponent n, and the green part is the factorial. So this particular part here is extra, right? So this e to the negative 0.2 does not appear in this sequence here. Okay? All right. So it says use this definition to evaluate this. Okay? So basically, what we could do is we could just like match up everything. So the summation of the yellow and green parts is basically equal to e to the x. And in this case, the x is 0.2. So basically, this part of it is equivalent to e to the 0.2. And that is multiplied times e to the negative 0.2, isn't it? Now, if you have two equal bases and each one has an exponent, you can add the exponents when you multiply the two expressions times each other. So you get e to the 0.2 minus 0.2, so you get e to the 0. And remember, e to the 0, or anything to the 0, is just 1. So basically, this expression is equal to 1. All right. Now let's look on, see what else we're supposed to do. Suppose the random variable x is the number of cars that pass a shop during the period from 3 p.m. to 3:03 p.m. The probability distribution for x is given by this function here, which happens to be the same as that function there, okay? Where x equals 0, 1, 2, 3, those are the number of cars. Explain why this is a valid probability distribution. Okay, so usually when they talk about making a function into a probability distribution, of course, all the coordinate points have to be positive because they have to be positive or 0 probability. But the other thing that we have to keep in mind is the area under the curve, or the adding up all the probabilities together, should equal 1. And you remember that if we add up all of these terms from 0 to infinity, we're going to get 1 because we just figured that out in part A. So it's valid because the sum of all the probabilities from 0 to infinity is equal to 1. Okay? All right, next one. So evaluate P, probability of x equals 0, probability of x equals 1, and probability of x equals 2. Okay, so let's try that. The probability as x equals 0 is equal to 0.2 to the 0 power, so that's 1, e to the negative 0.2, and 0 factorial. So that is equal to e to the negative 0.2. Okay, and what about the probability of x equal to 1? So for this one, it's 0.2 to the first power times e to the negative 0.2 divided by 1 factorial, which is just 1. So that's probability of x equal to 1. What about the probability that x equals to 2? That's equal to 0.2 squared. 0.2 squared would be 0.04 e to the negative 0.2 divided by 2 factorial, which is 2. So that could simplify into 0.02 e to the negative 0.2. Okay? All right. 3. Find the probability that at least 3 cars will pass the shop in the given period. So at least 3 cars means 3 or more cars. So the probability that x is greater than or equal to 3, that's equal to 1 minus the probability that x is less than or equal to 2, right? And we just figured out each component of x is less than or equal to 2. All we need to do is add up all these components here, these elements that we figured out, e to the negative 0.2, 0.2 times e to the negative 0.2, and 0.02 times e to the negative 2. So let's add up all those. It'll be 1 plus 0.2 plus 0.02 e to the negative 0.2. So that's equal to 1 minus 1 is 0. Negative 1 minus 1.22 e to the negative 0.2. Okay? So if you want to figure that out, you just put it in the calculator. So let's do the rest of page 1. So we're now in section 25D on page 790. They give an example of an experiment where you have a bag with 10 counters in it. What's a counter? It's just like a little chip with a number on it. So they got 10 counters, and they have the following numbers written on them. Since there's a disproportionate number of 1s, 2s, 3s, and 4s, the probability that you get 1, 2, 3, or 4 is not the same. 1/10, 4/10, 3/10, 2/10 in proportion to the number of times each number occurs, right? The possible results are shown in the table at right. So if you do 10 trials where you replace every time, then what you're going to see is 1 occurrence, 4 occurrences, 3 occurrences, 2 occurrences. So remember, back in the core part of discrete random variables, we got two formulas for the mean. One using frequency and number of trials, and the other one using probability, but basically they're the same, right? Probability is basically the same thing as the frequency of something happening divided by the number of trials, right? The mean, symbol mu, Greek letter for m, can also be represented by expectation, symbol expected value of the random variable x. So those two things mean the same thing. The variance can be calculated using either the frequency divided by the total number of trials, f divided by n, or using the probability p, which is equivalent to the frequency divided by n, just as the mean was. Okay, so do you see how in the mean we have two alternative formulas? One of them is frequency divided by n, and the other one is probability. And in the variance, we also have frequency divided by n and probability. The population variance can be expressed as var x or sigma squared, or as the expected value of the difference in the random variable and its mean. So the expected value of the difference of the random variable and its mean, actually squared. And the population standard deviation is the square root of the variance, so you can see that we just put a square root sign over some of the expressions that were given before. Notice that in this case here, the variable minus mu is quantity squared, and in this case here, it's x squared times the probability, and then minus mu squared, and they're separate, right? So these two are equivalent, and in the past we've done a derivation of this. Basically, you do FOIL on this, and when you do FOIL on it, some of the middle terms cancel out because you end up with something that averages to 0. So that's it for page 1.